Now we'll take a look at metabolic states and some of the things that affect our metabolic rate. So you're probably aware that your metabolism changes from hour to hour, depending on how long it's been since the last meal. If we have recently eaten or it's during a meal, we're in the absorptive or fed state. This is where nutrients are being absorbed and they're being used immediately to meet our energy needs. If we haven't eaten for a while, we're in the post-absorptive state or the fasting state. This is very prevalent in the late morning and the late afternoon and overnight. The stomach and the intestines are empty, and the body's energy needs are met primarily from stored fuels. So in the absorptive state, glucose is readily available for ATP synthesis, and it serves as the primary fuel, and it spares the body from having to draw stored fuels. Carbohydrates are absorbed sugars that are transported to the liver by the hepatic portal system. Most of the glucose will pass straight through the liver and become available to cells everywhere. However, there could be some glucose excess, which is then absorbed by the liver and is made into glycogen or fat inside the liver. And then the fat will be released into circulation, where it can be picked up by storage cells. Absorbed fats enter the lymph as chylomicrons, and initially they'll pass straight by the liver. But then lipoprotein lipase is going to remove the fats from the chylomicrons so that it can be taken up by tissues. Once they return to the liver, it disposes of the chylomicron remnants. Interestingly enough, fats are the primary energy substrates for hepatocytes, adipocytes, as well as muscle cells. Now, absorbed amino acids pass through the liver and go on to other cells, mostly for protein synthesis. However, in the liver, amino acids may need to be used for the production of fuel so that we can make ATP, or they may be used for fatty acid synthesis. Of course, some of them could also be used for protein synthesis within the liver. So the absorptive state is regulated primarily by insulin, which is secreted in response to elevated blood glucose and amino acid levels, because we need to package all of these materials away. It's also stimulated by intestinal hormones such as gastrin, secretin, cholecystokinin, and also a molecule called glucose-dependent insulinotropic peptide, or GIP. So insulin's involved in regulating glucose uptake by pretty much all cells. The exceptions would be neurons, kidney cells, and erythrocytes. And each of those have their own independent rates of uptake. They don't need insulin as a key to allow sugars and amino acids to become stored. So what sort of effect does insulin have on target cells? Well, first of all, it increases the uptake of glucose about 20-fold, causing blood glucose concentrations to fall as we draw glucose into the cells. It stimulates glucose oxidation and all sorts of other processes that are involved in storing any unused glucose, like glycogenesis and lipogenesis. Naturally, it inhibits gluconeogenesis because we're trying to remove glucose from the blood, not add to it. Insulin also stimulates active transport of amino acids into the cells and promotes protein synthesis, so building of our own proteins. It acts on the brain as an adiposity signal. So the amount of insulin will tell the brain how much fat is being stored. So let's think about this. Following a high protein or low carbohydrate meal, it may seem that amino acids would also stimulate insulin secretion, and insulin would accelerate both amino acid and glucose uptake. But if there's not very much glucose, then wouldn't that cause hypoglycemia? A high amino acid level stimulates secretion of both insulin and glucagon. Glucagon, you'll recall, is an insulin antagonist, and so it will act to add sugar to the blood if there's not enough blood sugar there. So the system takes care of itself. So the essence of the post-absorptive state is to homeostatically regulate blood glucose concentration within about 90 to 100 milligrams per deciliter. This is especially important for the brain because it can't use any alternative energy substrates, except in the case of prolonged fasting. The post-absorptive status of the major nutrients is as follows. Glucose is drawn from the body's glycogen reserves or synthesized from other compounds. And the liver usually stores enough glycogen after a meal to support about 4 hours of post-absorptive metabolism before it needs to do significant amounts of gluconeogenesis, where we're synthesizing glucose from other compounds. Fats. Adipocytes and hepatocytes will hydrolyze fat and convert glycerol to glucose. The free fatty acid molecules can't be converted directly back to glucose, but they can favorably affect blood glucose concentration through the formation of ketone bodies. The liver will oxidize free fatty acids to form these ketone bodies, which other cells can absorb and use as their source of energy. Or, of course, they could use directly the free fatty acids. This allows for the glucose-sparing effect, where most tissues can switch from using glucose to fatty acids, which leaves glucose available for the brain. Proteins, well, they are rarely ever used as fuel. They're only used when glycogen and fat reserves are depleted. And this makes sense because we don't want to go along digesting our own protein. Collagen is almost never broken down for fuel, but the muscle protein can go quite quickly once we're in a state of malnutrition. Cachexia is extreme wasting away that we see in cancer and some other chronic diseases, and it results from a loss of appetite, anorexia, as well as altered metabolic rates. The regulation of the post-absorptive state is maintained primarily by sympathetic nervous system and glucagon. As blood glucose levels drop, insulin secretion declines. The pancreatic alpha cells are going to secrete glucagon, and glucagon promotes processes like glycogenolysis and gluconeogenesis. So we're breaking apart glycogen to form glucose, or we're synthesizing glucose from other compounds, and thus we raise the blood glucose level. Glucagon also promotes lipolysis, the breakdown of triglycerides into glycerols and free fatty acids. Thus, we see an increase in free fatty acid levels. The sympathoadrenal system also promotes glycogenolysis and lipolysis. This occurs especially under conditions of injury, fear, anger, and other forms of stress. The adipose tissue is very richly innervated by the sympathetic nervous system. So in any situation where injury is likely to the tissues, we're going to mobilize all the stored energy reserves and make them energy to meet the demands of this repair. Adipocytes, hepatocytes, and muscle cells also respond to epinephrine from the adrenal medulla. Cortisol is released in response to stress. This also promotes fat and protein catabolism, along with gluconeogenesis, releasing glucose from its stored form. Growth hormones secreted in response to a rapid drop in glucose levels. This opposes insulin and raises blood glucose concentrations. So metabolic rate measures the amount of energy liberated in the body in any given period of time. It could be measured in kcals per hour or kcals per day. We can use a calorimeter to measure it, which is a closed chamber with water-filled walls. And these walls absorb the heat that's given off in the body, and we measure the temperature change in the water to give an estimate of metabolic rate. It can also be measured indirectly with the use of a spirometer that measures the amount of oxygen that a person consumes. Metabolic rate naturally depends on physical activity. It also depends on the mental state, the absorptive or post-absorptive status of the individual. Thyroid hormone has a big influence, along with some other hormones. The basal metabolic rate is a baseline standard of comparison. It minimizes the effects of all the variables. So we can measure basal metabolic rate, or BMR, in a relaxed but awake state after about 12 or 14 hours without food, in comfortable position at room temperature. The adult male basal metabolic rate is generally about 2,000 kcals per day, and it's slightly less for a female. So the basal metabolic rate is not the minimum metabolic rate needed to sustain life, because when one's asleep, the metabolic rate's even slightly lower than BMR. TMR, total metabolic rate, is the sum of our basal metabolic rate plus any expenditures that are voluntary, activities that result from muscle contraction. Things can raise TMR, like pregnancy, anxiety, fever. TMR is raised slightly after eating a meal. Catecholamines and thyroid hormones will also raise our total metabolic rate. And children have a high total metabolic rate, and it decreases with age. This is why, as we age, we may sometimes see a weight gain with no apparent decrease in food intake. There are many factors that lower total metabolic rate: apathy and depression, prolonged starvation, which is why in calorie restrictive diets, we might see that it becomes very difficult to lose body weight. That's because the body adapts and reduces its metabolic rate and increases fat storage to conserve body mass. So in general, calorie restrictive diets will actually cause us to gain more weight as soon as we stop the restriction. So all the enzymes that control our metabolism depend upon an optimal and stable working temperature. To maintain this, the loss of heat has got to match the heat we generate. If we have too low of a body temperature, it's called hypothermia, and this can cause slowing of metabolism and cause death because the enzymes don't function at their optimal rates. High body temperature, or hyperthermia, can also have metabolic pathways work out of sync. Some will race ahead of others, and it disrupts the coordination to a point that it also could lead to death. So thermoregulation is finding the balance between heat production and heat loss. Body temperature is normally about 98.6 degrees Fahrenheit. Now, there's normal body temperature is going to vary about 1.8 degrees Fahrenheit in a 24-hour cycle, with it being low in the morning and high in the late afternoon. When we consider body temperature itself, there's core or shell temperature to consider. The number 98.6 is what we get from shell temperature, taking the temperature in the oral cavity or at the skin surface. And it can be as high as 104 during hard exercise. Of course, it fluctuates in response to processes that maintain the stable core temperature. Core body temperature is the temperature of the organs in the cranial, thoracic, and abdominal cavities. We can best obtain this by using a rectal temperature. It estimates best the core temperature. In the adult, that varies from 99.0 to 99.7 degrees, so it's a little bit higher than the shell temperature. Most of the body's heat production comes from exergonic or energy-releasing reactions. These are processes that we've just been exploring, such as nutrient oxidation and ATP use. A little bit of heat is generated by joint friction, by blood flow itself, and by other movements of the body. But at rest, most of the heat is generated by the brain, heart, liver, and endocrine glands. Skeletal muscle contributes about 20 to 30% of the total resting heat. During vigorous exercise, however, the muscles produce 30 to 40 times as much as heat as the rest of the body, a significant increase. The body loses heat in three primary ways: radiation, conduction, and evaporation. So radiation is the emission of infrared rays by moving molecules. This means that heat is molecular motion. All molecular motion produces infrared rays. When infrared rays are absorbed by an object, they increase its molecular motion and thus raise its temperature. Since we're much warmer than the objects around us, we're usually going to lose heat by infrared radiation. So it removes heat from us and adds it to anything else that would absorb it. Conduction is the transfer of kinetic energy from one molecule to another molecule as they collide with each other. The warmth of our body is going to add to molecular motion and temperature of the clothes we wear, the chair that we sit in, the air that's around us, or the cold surface that we sit on. Conduction and convection are tied pretty closely together. Convection is the motion of fluid due to uneven heating. So it aids in conductive heat loss. As air is a fluid, it becomes less dense and rises as it's heated, and it's replaced by cooler air from below. Evaporation is when we change from a liquid form to a gaseous state. And it's the cohesion of water molecules that actually hampers their vibratory movements in response to heat input. So if the temperature of water is raised sufficiently, its molecular motion will become so great that molecules break free and evaporate. As they evaporate, they carry a lot of heat with them, 0.58 kcals per gram. So this change in state removes a lot of heat. So when a skin is wet with sweat, the evaporative means of heat loss will carry heat away. In extreme conditions like lots of sweating, heavy exercise, the body can lose 2 or more liters of sweat per hour, which dissipates up to 600 kcals of heat per hour. Evaporation will naturally increase with air movement. So again, convection comes up. You know, if you stand in front of a fan when you're wet, then you will become cool very rapidly. Forced convection is the rapid movement of heat-laden air away from the body, and it enhances loss by conduction and evaporation. But this would have no effect on radiation. As an example, a nude body in an air temperature of 70 degrees Fahrenheit would lose about 60% of its heat by radiation, 18% by conduction, and 22% by evaporation. If air temperature is higher than the skin temperature, evaporation becomes the only means of heat loss. That's why sweating is so important. Radiation and conduction would add more heat to the body than they remove from it if the temperature outside is higher than skin temperature. In very hot and humid weather, we're going to see that evaporation is hindered because there's less of a humidity gradient from the skin to the air. So thermoregulation is achieved through several negative feedback loops. First of all, we have the hypothalamic thermostat. This is the major area of thermostatic control in the body. It's in the preoptic area of the hypothalamus. Monitors the temperature of the blood. It receives signals from thermoreceptors in the skin, and it sends appropriate signals to either the heat loss center or the heat promoting center. The heat loss center is a nucleus in the anterior of the hypothalamus. The heat promoting center is going to be found more posteriorly in a nucleus near the mammillary bodies. When the heat loss center senses that blood temperature is too high, it activates the heat losing mechanisms. We'll see cutaneous vasodilation, increased blood flow close to the body's surface to promote heat loss from the blood. It'll also trigger sweating, which inhibits the heat promoting center and aids in heat loss through evaporation. When the heat promoting center senses that the blood temperature is too low, it activates mechanisms to conserve heat or generate more heat. We'll see the opposite effect, cutaneous vasoconstriction, so we pull the blood away from the skin, and therefore we lose less heat through the skin. If this is not enough to restore core temperature, then the body resorts to shivering thermogenesis. So shivering involves a spinal reflex. It causes the tiny alternating contractions of antagonistic muscle parts. Every muscle contraction releases heat from ATP consumption, thus adding to our body temperature. It can actually work to increase the body's heat production up to 4-fold. In non-shivering thermogenesis, we'll see the sympathetic nervous system and thyroid hormone increase our metabolic rate. This is a more long-term mechanism for generating heat. We burn more nutrients as fuel, which increases heat production, and we consume more calories. We could also see behavioral thermoregulation. So behaviors that raise or lower the body's heat gains and losses. This is things like adding or removing clothing, maybe running around to generate more heat. Sometimes we'll see disturbances in thermoregulatory mechanisms. Fever is a great example of this. Fever is a normal protective mechanism that should be allowed to run its course if it's not excessively high. If the temperature gets to 108 or 110 degrees Fahrenheit, this is very dangerous. It elevates the metabolic rate, it generates heat faster than heat-losing mechanisms can possibly disperse of it, and it causes a very dangerous positive feedback loop. If we get up as high as 113 degrees, we're going to see some serious metabolic dysfunction, definite neurological damage, and all of that can lead to death. If we have exposure to excessive heat, things like heat cramps, heat exhaustion, and heat stroke may ensue. Heat cramps are painful muscle spasms due to electrolyte imbalances. This is usually a result of excessive sweating. They occur especially when a person begins to relax after strenuous exertion and heavy sweating. Heat exhaustion results from severe water and electrolyte loss. We'll see hypotension, very low blood pressure, dizziness, vomiting, and sometimes fainting. Heat stroke, otherwise known as sunstroke, is when the core body temperature goes over 104 degrees Fahrenheit. And it's brought about by prolonged heat wave with high humidity. The skin is hot and dry. We'll start to see the nervous system dysfunctioning, a little bit of delirium, sometimes convulsions, or even coma. We'll see accelerated heart rate and tachycardia, hyperventilation, inflammation, and multi-organ dysfunction. Heat stroke is the most dangerous of thermoregulatory disturbances. It can cause death quite quickly. In the event of exposure to excessive cold, we may see hypothermia. This is a life-threatening positive feedback loop also. If the core temperature drops below 91 degrees Fahrenheit, our metabolic rate drops so low that the heat production cannot keep pace with the heat loss. Temperature falls even more, and then we'll see the metabolic rate drop even lower. Death from cardiac fibrillation may occur below 90 degrees Fahrenheit. Some people will survive body temperatures as low as 84 degrees in a state of suspended animation. We see this as a benefit in cold water drownings. Water temperature drops so low that the metabolic rate drops, and thus the effects of being without oxygen have less of an effect. When we see body temperatures below 74 degrees, it's most usually fatal. When someone's in a condition of hypothermia, it's very dangerous to give them alcohol, as alcohol accelerates heat loss by causing dilation of cutaneous vessels. So the old idea of having a sip of whiskey to warm up while it's cold out isn't really a good idea. So this brings us to the conclusion of our unit on nutrition and metabolism. Be sure to check in on the Anatomy and Physiology Revealed information and do your Connect, Learn Smart module, as well as completing the diagramming assignment for this chapter.